Here are some quick notes on photons and matter to accompany Chapter 3 of To Build a Star. So photons can interact with matter a number of different ways. If we want to divide this into three basic classes of processes, we have scattering. So a photon will change its angle and or its energy. We have absorption, where the photon is destroyed, and in nuclear physics we usually call that attenuation. Or we can have emission, where a photon is emitted, for instance, from a de-excitation, from an electron de-exciting from a higher orbital to a lower orbital. So when we have scattering and absorption, we can define each of these processes, the magnitude of that, using a cross-section. So it's sort of an interaction probability in a sense, and it has units of area. And so when you combine that with the number density of the environment, that describes the mean free path. So little n is the number density, so it's units of inverse volume, and sigma is the cross-section, has units of area. And that winds up being a length, known as the mean free path. So the mean free path, this is just the length for which the interaction probability is 1. So when a photon travels one mean free path, then you will have expected it to have interacted given a particular number density and cross-section for the interactions in that environment. So how do you calculate this mean free path? Well, let's just consider the three-dimensional case. So in 3 dimensions, your probability of a photon interacting is the area of the obstacles, or let's not just say photon, let's just say particles. So the area of the obstacles that your particle is going to encounter divided by the area of this object, so this particle, some object. The area of the obstacles, this is going to be equal to the volumetric density of those obstacles times the volume that's swept out by the object times the area of the obstacle itself, so the area that it's kind of encompassing as it's traveling a length. Okay, so that's the area of the obstacles, and then what's the volume swept out by the object? Well, it's the area of the object times the path length. And I think the book has a nice illustration of this where your objects are circles and they're going through a cylinder. Okay, so then we can plug numbers in here. So we have the volumetric density of our obstacles, that's the number density, times the area of our object times its length that it's traveling, so that's the volume that's swept out, times the area of the obstacle, and that is divided by the area of the object that's doing the sweeping. For this example, let's just say that it's the object area and the obstacle area are the same. So for instance, you have one billiard ball traveling through some three-dimensional volume with a bunch of other billiard balls, then those are going to cancel. Or I guess in any case these cancel. So your probability, right, is equal to the number density times this volume swept out, and that's got to be equal to 1. And so then the length that you've traveled for this interaction probability of 1 is equal to 1 over the number density times the area. And for a reaction, this area is defined as a cross-section, and so as promised, the mean free path is 1 over the number density times the cross-section. And for photons, we're going to, instead of having a number density times a cross-section, we're going to describe this with a volume or a mass density and an opacity. So the opacity times the mass density is just equal to the cross-section for the interaction times the number density. Okay. If you wanted to do this in 2 dimensions, then you basically would just take all of your areas and you'd turn those into widths, and all the volumes would turn into areas, right? So you downgrade everything by 1 dimension. So for scattering, this is primarily going to happen when photons are interacting with a free electron, because those free electrons cannot absorb the photon at all. When your photon energy is a lot less than the rest mass of the electron, which is about half an MeV, then what's going to happen is your scattering is going to be elastic, so kinetic energy is going to be conserved here, and this is known as Thomson scattering. So your photon's not changing energy here. So that's a way to calculate the energy. If you wanted to calculate the wavelength then has to be much greater than the Compton wavelength. It's just the reverse of this. We're just, instead of solving in terms of frequency, we have wavelength here. So wavelength has to be much greater than the Compton wavelength. That's Planck's constant divided by the rest mass of the electron times c. If you wanted to calculate this wavelength, probably if you're like me, you'd have to look up Planck's constant and the rest mass for the electron, and that's maybe kind of annoying. What you may remember, and at least if you do nuclear physics, there's some handy relationships you can remember, is you could multiply this by 2 pi c over 2 pi c. If you do that, then you get 2 pi times h bar. So that's h bar is Planck's constant divided by 2 pi. And you now have c, and in the bottom you have c squared. And why would you do that? It's because you may remember, this is something that's burned into my brain as a nuclear physicist, that h bar c is 197 MeV femtometers. And now we have things that I remember, is that the rest mass of the electron times c squared, that's 0.511 MeV. H bar c is 197 MeV femtometers, and you plug those in, and you get that the wavelength has to be quite a bit longer than 2.4 picometers. Now the wavelengths we're mostly talking about are the ones from the black body spectrum, right, which are in the ultraviolet and violet and radio and infrared and whatnot, and so they're much longer than this. And so indeed we're mostly in this case where Thomson scattering is going to be relevant. If we want to get the order of magnitude for this scattering cross-section, we can do the classical estimate, which remarkably is extremely close, as we'll see in a second. So we're going to just calculate the classical area of an electron as the pi times the classical electron radius squared. So the way that classical electron radius is calculated is you equate the electrostatic potential energy to the rest mass energy of the electron. So you say all that energy there in the rest mass is due to the electrostatic force, which isn't true, but you can do the classical calculation. And when you do that, let's just go to CGS so we can drop that pesky permittivity that no one ever remembers the value of. So then we have that the electron charge squared divided by the radius, so charge squared over radius, is equal to the rest mass. We can rearrange, and we have the radius in terms of charge squared over rest mass of the electron. If you don't want to, you might remember this charge in terms of coulombs, but then how do you deal with that in terms of mass? It's kind of a pain. So again, we can use a trick. We'll multiply by h bar c over h bar c. We can recognize, again, as a nuclear physicist, it'll be burned into your mind, E squared over h bar c, that's about, that is the fine structure constant, which is about 1 over 137. H bar c by itself is 197 MeV femtometers, or very close to that. So you plug those numbers in, and you get that the classical electron radius is about 2.8 femtometers, which is obviously not, it's a point particle. It doesn't have a radius. This is more like the radius of a nucleon. But in any case, you take this and plug it into your area calculation. So then your Thomson scattering cross-section is that classical area of the electron, which is about 2 times 10 to the minus 29 femtometers squared. Remarkably, when you go through fancier stuff and you do electromagnetism, you get a factor of 8/3 out front of that, and that winds up being correct, which is kind of amazing. So you can also absorb your photon. There's different ways to do that. One of them is so-called free absorption. So your electron is not bound to an atom at all, so the gas has to be ionized. And basically a photon comes in and the electron absorbs it and gains energy. So that's how the photon is destroyed. It's basically the reverse of bremsstrahlung that you might have read about before. You can have bound-free absorption. So a photon comes in and causes the electron to be ejected from the atom. It basically ionizes it. So it has to be cool enough that you have non-ionized atoms. And you can have bound-bound absorption, where the photon comes in and instead of the electron being ejected completely from the atom, instead it's just excited to a different state. So from one state to another state. So remember that we defined, instead of using a cross-section, we use an opacity. There are many different contributions to the opacity, right? We just learned about scattering and the different absorption processes. And each of them are going to be wavelength dependent. So, for instance, you have your bound free is this smooth red curve, but then when you go to bound, you get all these crazy spikes, right? It's kind of nuts. So lots of different contributions to the opacity. And there's this rough temperature and density dependence that Kramer worked out a long time ago for the free and the bound free. Bound's a lot more complicated. We can combine, well, first, these opacities are wavelength dependent, as you can see in the plot in the upper right. So you can integrate these over wavelength, and then you combine the various opacities into a so-called Rosalind mean opacity. This has to be calculated numerically, and tables exist to do this for assumed compositions. So you can, and assume nuclear and atomic physics data, so you can download these. So for instance, one, getting older but still considered kind of state-of-the-art opacity library is the Opal set of tables. And what's shown here is the Rosalind mean opacity as a function of the temperature. The gray curves are different densities that are being assumed, and the composition here is roughly the solar composition. And so at very high temperatures, the opacity is dominated by the electron scattering. As the temperature decreases, you have this temperature to the -7/2 thing going on. So that's your free and your bound free that are happening. You peak where you have things like a lot of absorption from iron. There's lots of transitions in the transition metals. So you peak there, and then you can decrease as you go to these lower temperatures. That should be H- superscript. As you decrease, the H- is the only ion that's left, and the abundance of that ion decreases strongly with temperature, and so that goes down. And so you can see these opacities, are kind of complicated, and we'll usually use either a very simple approximation or you go, sometimes straight to the tables. And finally, the photons can be emitted, right? So for instance, we saw that you can have these bound-bound transitions where you excite an electron to an excited state and absorb a photon. Well, that electron can then de-excite and emit a photon, and that photon will go back into the environment. Electrons can undergo Bremsstrahlung that you're familiar with. So when an electron decelerates in the presence of an ion, so it turns or slows down because of a Coulomb field, then photons are emitted. And why do we care about this emission? It has to be taken into account in our sort of photon economy, and especially if we're thinking about a cone of light, then light from a neighboring cone, if you will, can be scattered into or out of that cone. And that is it for these quick notes on photon and matter interactions.